Let's change tacks. We had, in our picture from Wednesday, we had graphs with cut vertices and graphs with bridges. There are bridges in G1 and G2. There's a cut vertex in G3. But G4 through G7 do not have such options. There are no cut vertices in any of these four. A graph with no cut vertices is called non-separable, assuming it's connected to start with. So that means, what can you guarantee me about all of the vertices in such a graph? And as a consequence of that, every pair of vertices must be on more than one path they must be part of a cycle. They must be on some cycle. I don't know what cycle, but every pair of vertices must be part of a cycle. As long as I have at least three, right? So if I only have two, well, then it could be a K2. Let's look at more than that. All right, wait a second. Let me go back to my pictures. On page 107, pick one of the graphs that we said was non-separable, 4, 5, 6, or 7. And let's pick any two vertices on one of those graphs. Is there, between any two vertices, a cycle? Well, I would hope so in this case, right? Because that graph is a cycle. And therefore, no matter which two vertices you pick, they're on the cycle. And here, no matter which two vertices you pick, they're adjacent, right? But everything's connected to everything else. So go directly from one to the other and then go around the outside the way you want to go, clockwise or counterclockwise, and you're there. What about here? Well, yeah, because everything's around the outside, right? But I don't have to use the outside. If I picked these two, I could use this little upper triangle, couldn't I? So it depends on which cycle. It didn't say what cycle, just a common cycle. What about the middle vertex in 5? How so, Reese?
You can pick anything above it, and it's on like that diamond shape.
So no matter what two vertices you pick, there's a cycle that contains both of them. A set of examples is not enough. Now, it's an if and only if. I have to do two of them. One of them is easier than the other. We'll do that one first. So I'm going to start with the assumption that I have a graph with at least 3 vertices, and every pair lies on a common cycle. What I want to show is that the graph is non-separable, which means I should not be able to find a cut vertex. Proving that something does not exist is hard. So let's suppose there is one and find a contradiction. Every 2 vertices lie on a common cycle, yes? And I have a cut vertex. Let's pull the cut vertex out. What happens? What do I know about G minus V? Disconnected. It might create more than 2, right? But at least 2. It's disconnected. So let's put V back in. But pick a vertex from each side of the cut vertex. Matter of fact, we'll name the cut vertex V. I just said that, but I didn't actually write it down. V. Let U and W be vertices from different components of G minus V. What do we know about U and W? They're on a common cycle in G. Let's call this cycle C. Why is that a problem? Just the mere existence of this cycle brings me to my contradiction.
Assuming you and V were going to be on the same cycle. Even if V is in that cycle, we can go around the other way.
Oops. I now have two paths between U and W, only one of which contains V. Because in a cut vertex, every path has to go through that cut vertex. You just found me a path that doesn't. It can't be a cut vertex if everything lies on a common cycle. That's the, quote, easy version, the easy direction. Now I want to go the other way. Suppose the order of my graph is at least 3 and G is non-separable. No cut vertices. Wait, no cut vertices means no what else? Bridges. All right. There's a construction in this proof. I need to find the cycles, right? I want to show that every two vertices have a common cycle. Every two. This is going to suck. Let's do the same thing we did before. Let's suppose there isn't one. Suppose you've got one pair of vertices. They don't have a cycle. Then we'll come up with a problem. Suppose U and V. I should be very careful, a common cycle. So I have some vertices that don't share a cycle. I want the two of those vertices that are closest together. Let U and V be such a pair of vertices with minimal distance. So DUV is as small as we can get while still having no common cycle. Smallest distance you can have on a graph if my edges are adjacent, right? But that means that the edge UV is in the edge set of my graph. Why does that force there to be a cycle? Because there's no bridges. If there was not another way to get from U to V, then UV would be a bridge. And we said right here, there are no bridges. If there's not another way to get from U to V, I've got a bridge. Now that's only in the case if the distance is 1. So if I'm doing it by cases, my next case is that the distance from U to V is bigger than 1. Again, I need a name for this distance. K. That means there's a path of length K from U to V. All right. From U to V is K steps. So look at the penultimate step. Vk minus 1. What do you know about those two? I'm sorry? It. What it? Yes. The distance from U to Vk minus 1 is K minus 1. Took me a minute to parse that, Jonas. Sorry. Good. So what? Now that I know that, what does that help me with? It actually does help me with something.
We wanted U and V to be the small.
I found something that's smaller, but U and V were the smallest distance that did what? Which means that VK minus 1 and U are on a cycle. I also know VK minus 1 is not a cut vertex. Yes? And that means there's at least one other path from U to V that misses that vertex. Now that's a path. I already used P. We'll use Q. So here's an interesting point. We picked a path P of length K. There must be some other path Q that avoids VK minus 1. That's cut vertex. But I know U and VK minus 1 are on a common cycle. Let's think about this path Q. I start out at U. I start working towards V. Maybe I'm on the same path as V for a little while. At some point, I have to veer off it because I have to skip VK minus 1. Maybe I do that right at the beginning. Maybe this path is completely different. But maybe it isn't. Maybe for a while it's the same. Somewhere along that path, I branch off. U is on my cycle. The cycle between U and VK minus 1. I start going from U to V. Maybe I'm on that cycle for a bit. Maybe I'm on the path. Somewhere I have to get off the cycle because the cycle is going to hit VK minus 1. And I want to avoid that with Q. So I look at my cycle, and then I look at this new path. I say to myself, where do they come apart? Where do they separate? Let's name that vertex. X. So I start walking along my cycle. I hit vertex X. A picture should help. Let me draw a picture. U and Vk minus 1 are on a cycle. There's my cycle C. But to go from U to V, I have to have a path, Q. And Q separates from my cycle here. See how it avoids Vk minus 1? So this upper part of the cycle and this extra curve, that's Q. Let's call the piece of it from X to V, let's call this part Q prime. So we start off on the cycle, we do this part of the cycle, and then we jump off and we take this route Q prime. So far, so good? But I just found a way to get back to U. Because what do I know about Vk minus 1 and Vk? They're on a path. They're adjacent to each other on the path P, which means there's an edge there. Now, ready for the amazing part? Do you see a cycle that connects U to V and back to U? Yeah, it's just a bunch of different pieces. I go from U to X, from X to V, from V back to Vk minus 1, and then I finish the cycle. Hey, wait a minute. I thought you said these two didn't share a cycle. And all we did was say if there were any vertices that didn't share a cycle, start with the two that are closest together. Then I built a cycle that they share. The only way this fails is if there are no vertices that already don't share a cycle. We said right back up here, U and V be a pair of vertices that do not lie on a common cycle, and then we built a common cycle. Now I will freely admit that this picture, when I looked it up in the book, drove me absolutely apeshit. Because I couldn't figure out how the hell that picture was supposed to show me anything. Until I drew those stupid little arrows on it and understood that I had built a cycle. Oh no, I can get there from here and back without repeating a stop. Okay, so here's connectivity a new way. We have separable ideas, and then we have this non-separable idea. If I have a bridge, if I have a cut vertex, if there's something I can pull out, the whole thing falls into pieces. No, there's a cycle between every two things. Always a redundant path. Preserve connectivity even when I pull something out. Questions? Because this is weird. I really want to punch some of the people who do grammar in mathematics in the face repeatedly. The textbook wrote this sentence, and I wanted to reach out to either Gary or Ping, the authors, and whack them one. If your graph is not non-separable, what should you call it? But they don't! And I don't know why. So let's suppose we have a separable graph, damn it. Well, that means there are pieces that I could take apart. There's a cut vertex or a bridge or something there, right? But in addition to that, there will be a subgraph of G that is not separable. So even if my graph itself is separable, there's a subgraph within it that's not separable. So let's make one of those subgraphs and make it as big as we can. A maximal, non-separable subgraph of G is a block. Maximal. What does maximal mean here? It means if I add any other vertices or additional edges from G, I include a cut vertex and or a bridge. Another way to say it is that B is not a proper subgraph of any other non-separable part of G. Make a copy of the picture. Fumble. Here's a graph. How many cut vertices does this graph contain? Please note, this graph has one bridge. So there's at least one. What are they? Bottom, middle, this vertex? This one. Why is this one not, even though it's on the bridge? Right, it's a leaf, and leaves are never cut vertices. So I have two of them. I have this one. No, let me use U. And I have, what was the other one? Great. Pick any other vertex other than U or V. And let's start looking at the biggest subgraph we can get without crossing one of the cut vertices. So if I start anywhere over here on the left, this set, including the cut vertex itself, that's a block. I'll call it block 1. What's another block? Sorry? The C3 triangle, right? So way over here from V, there's a block. You moved all the way to the right. I don't want to number that one yet because there's more in the middle. I'm sorry?
It'd be easy to say that one then. Right above you.
Aha! To the right of U and above V should also be a block. Notice each block contains a copy of the cut vertex it is adjacent or incident upon. There's one more block. Bridge. Fourth. And in some sense, you've seen this before. Who in this room has assembled Lego sets? We've an exploded view, don't we? Things that overlap would be repeated in each part. You build this part, you build this part, and then you align those bits and snap them together. In a Lego diagram, there'd be dotted lines between those pieces, wouldn't there? It's an exploded view. A disconnected graph has components. A separable graph has blocks. If my graph is connected and non-separable, it's one block. If my graph is connected and non-separable, it's one block. Any connected graph that has cut vertices is really a glued together set of blocks. This is not the only way to define a block. Matter of fact, this is the strictly visual way to define a block as a maximal non-decomposable subgraph. The other way to do it is with the proof we just did with our common cycles. Pick any two vertices in our graph, labeled or unlabeled. In that top picture, pick any two vertices. This graph has cut vertices. So I know not every pair of vertices will be on a common cycle. Pick two vertices that are not on a common cycle. What do you know about them? You're looking at me like I just asked you to recite Albert Einstein's special theory of relativity. I promise this is not as psychotic a question as you think it is. Start these. Pick two vertices. Which two did you pick? This one? Why do those not lie on a common cycle? In order to go from here to here, I've got to go through V. That means there's no cycle, because even if I went in a different way, I'd have to, U. I'd have to go back through U. I'm not allowed to repeat an edge or a vertex on a cycle. I have to cross the cut vertex. If you pick two vertices that are not on a common cycle, must be in different blocks. Which means the idea of being on a common cycle is a way to define a block. All vertices that share a common cycle with this one. I'll use the one you picked. All of them must be in this block. So let's say two vertices are related if they share a common cycle. I'm back in discrete. If I have a relation, what do I want to know about it? The things I always test about relations. All of that fun stuff, reflexive and symmetric and transitive. And if so, this is an equivalence relation. Every vertex shares a cycle with itself, right? If I can go on a cycle from U to W, then I can go on that same cycle from W to U, can't I? If I can go from U to W and W to V, I can go from U to V. Just glue the two cycles together. Which means we get a partition of the vertices into equivalence classes. But the cut vertices themselves overlap. They're in more than one pile, aren't they? which is why we have multiple copies of them in the blocks. What really happens is that this should be a relationship on edges rather than a relationship on vertices. And then each edge only appears in one block. Every set of blocks is edge disjoint and shares at most one vertex between blocks. Yay! On the first exam, you were asked to build up graphs, right? We took the union, the sum, the product, we built graphs up. What I'm doing now is the reverse, decomposing my graphs to figure out what's going on inside a given graph. If I know what the pieces are, I understand the structure of what's going on a little bit better. I can look at the more complicated, complete, large graph as a sum, a union of all the blocks with the appropriate overlap. This allows me to do a deeper dive into what's going on inside a graph. More on that when we get there. Have a wonderful break, everybody. See you later.